So we're going to take a look today at the Caesar shift and some other elements of elementary cryptography. So the classical sense of cryptography, the classical goal, is to obscure the contents of a message so that only people who are supposed to be able to read the message can read it. So this idea of confidentiality, so that only certain people who have inside knowledge are the ones who are allowed to read the message. And so in this sense, a message may be obscured in some particular way, and then there is an extra piece of information called a key that if you know the key, then you can unobscure, you can unhide the message, and so you're able to read it. If you don't have the key, then the idea is that you're not able to read it. If you do have the key, then you are able to read it. So this is the classical goal of cryptography. Has been in place for thousands of years. The earliest known examples that I've seen in reading date back to about the year 1900 BCE. And this kind of sense of replacing what is people expect with something that's not expected, so that they're only able to understand it if they are supposed to be able to understand it. And so to think about this goal, this is again the classical goal. There are more modern goals of cryptography now that involve other aspects, like making sure that people are who they say they are, or that if someone sends a message that they can't later say, hey, that wasn't me. There are a bunch of other issues around modern cryptography, but we're going to focus today on this classical goal. So the primary methods of obscuring the contents of a message. Now, in our case, we're talking about written messages. We're going to write these messages in English, and we're going to then obscure these messages a little bit. We're not doing modern cryptographic techniques that are secure by any means. But for our purposes, written text being obscured in some way. One way to do this is by the method of substitution, where you have your original written text and you replace letters with different letters. So an A might become something else, a B, whatever it becomes. Each letter being replaced with something else. Another way to obscure the contents of a message is by transposition. And this is where you change the order of the letters. So by itself, transposition, the cipher text, as it's called, the obscured message, has the same exact letters, they're just in a different order. But the way the order has been modified, if you know the secret, if you know the way to decode, in other words, if you know the key, you can unscramble them, put them back in the correct order. With substitution, if you know the key, you can replace the letters in reverse order to put them back in the way they need to be. Now, modern cryptographic systems will often do a combination of these things, substitution and transposition mixed together in various ways, much more complicated ways than we're going to talk about here, in order to obscure the contents enough to be able to be secure against much stronger resources. So our examples today are going to be very straightforward. We could break these by hand. These aren't things that we have to, that we would never use these in real life setting. But these are to develop some ideas that are part of modern cryptographic systems. So the aspects of cryptography, people who are supposed to read the message need to be able to read it, so we must be able to recover the original message with the key. And it should be difficult to recover the original message without the key. So the idea is that in a real life setting, since you only want certain people to be able to read the message, people who have the key or who have access to the key should be able to recover the message and read it. And if you don't have that key, then you shouldn't be able to. The systems we're going to talk about today can actually be broken without ever learning the key. There are easy enough patterns and aspects of written language that these are rather weak methods, but we are again looking for the general idea of what is going into a deeper level. And so we're not going to worry about it being difficult to recover the original message, but that's the overall actual goal. So the first one we're going to talk about dates back to Julius Caesar. It's called the Caesar shift. And the idea of this was that Caesar wanted to send messages to generals, but didn't want to risk just writing a message and sending it on the way. And so the idea was that we begin with the plain text, just the message that you want to be sent. And so let's say we have the message linear algebra. We're going to encode this message, and the Caesar shift just says, okay, let's take each letter and shift it by a predetermined key amount. Let's say we're going to shift it +3. So that means that every letter is just going to be shifted to a new letter that's 3 letters later. So this was the kind of classical Caesar shift approach. Every letter gets shifted by 3 letters. And so in this case, the L is going to be shifted 3 letters later, M and O, so L becomes O. And then we go through all of the other letters. So for the linear part of our message, we see each letter just gets shifted to a letter that's 3 letters later. In this setting, in the Caesar shift, spaces stayed spaces. So and if there was any punctuation, it would just be the same punctuation. It's just the words themselves that get shifted. And so if we do this process, then linear algebra gets shifted 3 letters later. And the red text on the screen is the encoded version of that plain text. So this is what we call the ciphertext. The black plain text letters become these red ciphertext. And I'm just putting them in red and black so we can easily distinguish which was plain text and which was ciphertext. Of course, in this case, we can tell, but sometimes a word might get transformed into another actual word. It's just that one of those words is the real word, the plain text word, and the other is the encoded word. In this case, none of the ciphertext is actual words, but it is possible that it could have been. The thing that happens in this +3 shift, for example, when you get to the end of the alphabet, then the letters have to wrap around. So X then will become A, Y is B, Z is C. And so it just wraps around, +3 wraps back to the beginning. Okay, so traditionally in the encoding, as we mentioned, the spaces and punctuation remained unchanged. The text in the traditional sense is not case sensitive. We were just dealing, say, with all capital letters, all uppercase. We will look at a broader sense of this. Spaces and punctuation by the end of today will not remain unchanged. And the text will be case sensitive, but at the beginning, we'll go with this. So the idea, we have A through Z, the 26 letters of the alphabet. And so with the +3 sense, we can write, we can make a table and list the new values underneath. And so this would say the +3 in red, A would become D, B would become E, and so on. And so to encode, we could just have all 26 of these written out. If we have plain text in black, we would look at the red letter underneath it and write that red letter down, and that would become the cipher text at the end of the process. But the Caesar shift doesn't have to be a +3. Here, all of these letters are 3 letters later. We could pick whatever value we want for the shift. And so, for instance, if we decided to shift it a different amount, then we could say A becomes H. And then each letter after that. So here is a 7, a 7 shift, a +7. We could do any kind of shift we like. A becomes whichever letter we want it to be, and then everything just falls into place afterwards and wraps when it gets to the end of the alphabet. So if you think about this, then we have the situation of one shift, and you could imagine following that with another shift. So we could imagine that the red letters are now the plain text, and the blue are a new ciphertext, a new Caesar shift. But one Caesar shift followed by another Caesar shift is still just another Caesar shift. And so we don't really have to worry about for individual situations of we're not going to gain anything by encoding something twice in this sense, right? If we encode it by Caesar shift and then do another Caesar shift to that, we could have just done one single shift from the beginning and end up with the same ciphertext. So we may not know the exact key at the end that if somebody did it in 2 steps, we can figure out what it was without actually knowing that they did it in 2 steps. We can go from the plain text to the ciphertext and back to the plain text if we know one overall approach that will get us there. So we may not know, oh, this person did it in 2 steps rather than in 1 step, but with a Caesar shift, repeated Caesar shifts, you can make that happen in 1 step. Now, there's only a limited number of possible different shifts then. So if we don't shift at all, then the plain text and the ciphertext are exactly the same, so that's not very interesting. If we shift forward by 1 or 2 or 3, we could shift forward all the way to A becoming Z, but then after that, it just wraps back around and we're back to the beginning. So there's a limited number of shifts that are possible. Again, the traditional sense is a +3, but it can be any choice that you like. Okay, so we encode by replacing the black letters, in this case just for color coding. The black letters get replaced with the red letters, or the black letters get replaced with the blue letters, but we're not mixing and matching right now. If we decide we're going with red, if we're going with the +3 shift, then we're always using the red line. If we decide we're going with a +7, we're always using the blue line. If we decide we're going with a plus whatever, we'll go with whatever line that would correspond to. Okay, now for decoding, we said we have to be able to get back to the original message from the ciphertext. So let's say we have some text here, and we say, let's decode this text. Okay, so what's the idea? The idea is we need to know the key. So we need to know what the shift was that got us there, and then we're going to move. If we move to the right to get to the ciphertext, we will just move to the left to get to the plain text. And so basically what we can do is we can swap the roles of the plain text and the ciphertext rows in the encoding process and say, all right, well, let's replace the red, or if it was the blue, let's replace that with the black. and that will get us back to the original. So you can decode this message and see what it says. Okay, now when we're actually encoding, we want to be a little more precise, and we want to be able to write some code to do this encoding for us. And so it turns out to be a lot easier if we do things numerically. Rather than thinking about the letters themselves, if we turn those letters into numbers and do calculations on the numbers, and then turn those numbers back into letters later. So again, we have these letters, and the easiest way to do this numerically is to just number things 0 to 25. There are 26 letters. Number them 0 to 25. And then we can do all of our numerical calculations mod 26. The modulus 26 will do that wraparound. When you get to 26, you're back to 0. It starts over. And we'll do all of the calculations in this mod 26 world if we're just using the letters, capital letters A to Z. Okay, so some number x becomes x plus k, where k is our amount of the shift, mod 26, and then we figure out which letter did that correspond to. So the number 2 becomes whatever number it became, and so that would mean the letter C becomes whatever letter that corresponds to. So in the case of the k equals plus 3, the Z is 25, so 25 plus 3 mod 26, well 28 mod 26 is 2, and 2 corresponds to the letter C, and we saw in the previous list that the Z becomes C in the plus 3 shift. So we don't have to keep track of where did we wrap around to and so on. If it's only plus 3, that's not so difficult. But if we had a plus 17 and we were looking at what does R become or something, some letter, what does it become? It's easier if we do this with this numerical calculation and then translate it back into letters. Okay, so we want to be able to do this even more generally. And so with the ASCII representation, we're going to be able to handle other things and not have to keep track of just the 25, 0 to 25, but we can keep track of kind of a lot of different characters that can be written, and we can encode messages and use all of the printable kind of characters. So the ASCII, the standard, the American Standard Code for Information Interchange, is a 7-bit character code. So with 7 bits, we are able to use values from 0 to 127, if we convert those to decimals, 0 to 127. And so the values 0 to 31 are for various unprintable control characters, things that might involve showing things on screen or using a printer and so on. So we're not going to worry about those values. We're going to worry about the values that are printable. And so the values numbered 32 to 126 are a bunch of different printable characters, and then 127 is delete. And so the list of characters that we care about are the ones 32 to 126. So there are 95 of those printable characters that we are going to focus on. Now there's an extended version of this, and that's an 8-bit character code. And the 8-bit character code then allows us to go on up to values of 255. So we have 0 to 127 are the same as before, and then the extended version goes on. And this includes a bunch of other printable characters. A few of these numbers aren't used, and so various reasons that they're not used, but characters such as the euro symbol and the pound and the copyright, the plus or minus symbol, fractions like 1/2 and 3/4, and then a bunch of other characters, special characters, accents in various ways, and so on, are included in this extended version. And then there are other kind of character encodings that are possible to be able to do a bunch of other situations, but we're just going to focus on the standard ASCII 0 to 127 in what we're talking about now. Okay, so in this table, you can see that these are the printable characters that start with a 32 and go up to 126. And so, for instance, 32 is the space. That's a printable character that you actually see the cursor move over. All of the symbols and so on. In the up to 64, a bunch of different printable symbols. The numbers are in there, and so on. Starting at 65 are the capital letters. They go up to 90. And then there are some other printable symbols, and the lowercase letters start at 97 and go to 122. So you notice in each of those cases there are 65 to 90. That's 26 letters in there. 97 to 122, also 26 letters there. Uppercase, lowercase, and the other printable kind of characters in the ASCII table. Again, there are other characters that can be printed if we go beyond that, and we would still be able to access those, and we can utilize those if we wanted to with our code, but we're going to just stick with these printable characters here. So from 32 to 126, that means there are 95 printable characters that we care about. Okay, so to use this, we need to be able to go from the letters, I said letters, but characters, to numbers and then back again. So we need to be able, in this process, to be able to have a character and look up the number from the table, or we have to be able to have the number and look up the character, because in the calculation, when we went from Z to the numerical calculations and then back to the C at the end, we need to be able to go from the letter to the number so we can do the calculations, and then at the end, when we have our answer, we need to be able to go back to the corresponding letter. So we need to be able to move back and forth in this. And the nice thing is that Python makes this really easy for us. Python gives us two functions. One is called ord. So you say ord of a character. So this character here needs to be an actual character, right? So I put the word character in there, but we're going to give it a printable character. So this is a string, a single character string. And we say, hey, what is the number that corresponds to that? And so if we say ord, say A, capital A in quotes, say what is the number that corresponds to the capital letter A, then we will get back 65. That is the number that corresponds to that letter. So that lets us go from character to the number. Then, to go from the number back to the character, we have this char, CHR. So you give it a number, and you say, here's the number, what is the letter? What is the character? Again, I'm saying a letter. It doesn't have to be a letter. It's one of the 95 printable characters. You say, what is that character? And we get back that character that corresponds to that number. So character to number, you use ord. Number to character, we use char. I said integer here, and it is an integer that we're talking about, but it doesn't have to be a decimal number. In Python, we can give it a binary number. We could give it a hexadecimal value. We can say, what is the character that corresponds to this particular number? We're just going to do it strictly in decimal numbers, thinking about the numbers from 32 up to 126. Okay, so let's look at a Python implementation of the capital letter version of this. Okay, so we're going to create a function called Caesar, and we're going to give it text, and we're going to give it a key. Now, we're not doing any error handling in this. We're not doing the doc strings and so on here in this presentation. We're just looking at if everything is working correctly. So what is the text going to be? The text is going to be a text string, and the key is going to be a number. The numbers that make sense would be things that make sense for a shift. It doesn't make sense to do a Caesar shift of plus 400 because what can you really only do? You can really only shift from 0 to 25, or you could go backward. We could have negative values for the key. But again, it only makes sense really in terms of thinking like indexing, negative 26 to 25. Then we're repeating ourselves. But the key can be any number that we want. Okay, so we're going to do this in kind of pieces. We're going to build a list of numbers, and then we're going to turn that list of numbers into the ciphertext, into a string. So we're going to start off, and I've just called this list encrypted. This is going to be, our text is going to be turned into a list of numbers. And so we're going to look at each character in the text, and one character at a time, because that's the way this numerical conversion works. We're going to look at one character at a time, and we're going to get its value. Okay, so now we need to look at what's happening here. We have the number that corresponds to that character, and the number that corresponds to that character is then, we're thinking of capital letters right now, so that number is going to be between 65 and 90 inclusive. And so if we're going to do our 0 to 25 enumeration, we need for that value to be shifted over so that it's between 0 and 25. So we're going to take that number and subtract 65 from it so that we have moved our numbers 65 to 90, we've moved them down into the 0 to 25 range. And then we're going to add the key to that. So that's where our shift is involved. And then we will do the mod 26. And you remember that mod 26 is done with the percent sign. So this is going to be the mod 26. So that's given us our number from 0 to 25. But then we really still need that number to be between 65 and 90 so that Python can recognize what the letter is. So at the end, we'll add the 65 back to it, right? So we did shift it over so that our numbers are between 0 and 25, add the key, do the work there, and then shift it back at the end so that we have an actual character that's another capital letter in place. And then we're just going to append that value to our list that we've called encrypted. So we take that value and we throw it into the list. Go to the next character. Do the same thing. Next character, and next character. All right, so now what we have is we have a new list of numbers. This list of numbers, all of them will be between 65 and 90. Now, right now, we do have a bit of an issue. We can't handle any spaces or special characters. These are only capital letters that this code will work with right now. We could modify this and say, okay, if there's a space, we say we're going to maintain the spaces in the traditional sense. We could maintain the spaces. If we see a space, then that value becomes 32 because that was what the space was, and so it just stays at 32. But again, we'll just, we're going to go for the full implementation in a few minutes. And so we just, when you test this, just don't put in anything that has spaces or anything that's not capital letters. Okay, so now then, we're going to create the ciphertext from this list of numbers. So the ciphertext is going to be a string. So we start off with an empty string. And we're going to loop through everything that is in our list, the encrypted list, right? So we're going to do this by decided to do this looping by index. We could loop by value, but we're looping by index. And so we're going to take the value from the list, and we're going to turn it back into a character, right? So it's a number, and we're going to turn it back into a character and add that on to the end of the string, concatenate that to the end of the ciphertext string. And that's it. Return ciphertext, and we will have gone from plain text and a key to ciphertext. Okay, so pause the video and try this out. Encode some things, decode, well, can't decode yet. We haven't talked about what to do with decoding, but you think about what you could do to decode. So encode, you put in the plain text and the key, and then you will get back the ciphertext. To decode, what would you do? Put in the ciphertext as the text, and what would you use for the key? If we used +5 to encode, we would use what to decode? Okay, so pause the video and experiment, play with this implementation just for a bit, and then we're going to expand this to go on to kind of all of the characters in the 32 to 126 range. Okay, so you took some time, you got some things to work, and so now we have the code in front of us, and we are going to modify this now so that it works for all of the printable characters numbered 32 to 126. Okay, so what's going to happen? Instead of just looking at numbers that begin at 65, we're looking at numbers that begin as small as 32. So the -65 right here, we need to change that. Instead of making 65 look like 0 temporarily in our calculation, we need 32 to be the 0. So we need to change the 65 here, and we need to change the 65 at the end. But now, rather than there being 26 characters, we're going all the way from 32 all the way up to 126, and so we need to change our mod as well. So it's not mod 26 anymore. We need to account for what all possible, the number of possible values there are. So we need to change the 65s, both of those, and we need to change that 26. And so here we will have the full implementation of the Caesar shift. The text can be the actual plain text, or it could be the ciphertext, and the key is the appropriate key for either encoding or for decoding that particular message. Now, there's a big limitation of this process. The Caesar shift is a monoalphabetic substitution cipher. What does that mean? Monoalphabetic means that every plain text letter becomes the same ciphertext letter every time. So if we have an A and it became an H in one place, it becomes an H everywhere. It's monoalphabetic. It's a one character substitution. The A always becomes H in that example. The downside to this is that the letter frequency is preserved. And so in a written language, a language like English, French, lots of languages, for example, the letter E is the most common letter. So if you have a lot of text, then you can look at this message that's encrypted with Caesar shift, and you're able to figure out that, oh, well, this letter E is not showing up very often, but in this case, H is showing up a lot. And so in the +3 Caesar shift, H would become the most common letter overall. Now, not necessarily in specific text, but if you had a lot of text. And so you might be able to break the code without really figuring out what the key was directly, but being able to determine some other aspects, patterns in the language. And so the Caesar shift is not secure at all. You can actually break a Caesar shift with paper and pencil. You don't have to have a lot of computing power to be able to break the code. But this idea of there being patterns that are there that exist will definitely give code breakers an advantage, and even in more elaborate versions that are more involved than the Caesar shift, there are lots of times that certain patterns are there that we don't necessarily realize are there. We think the method is good, and it turns out that there's ways around the key. There are ways to recognize other patterns. Maybe it's not single letters, maybe it's pairs of letters or triplets, various aspects that make the patterns become more visible and give the code breakers an advantage. Well, the Caesar shift from about 2,000 years ago or so, people realized, okay, this isn't as good as it could be. And so in the 16th century, the Vigenère cipher is attributed to Vigenère, but it's an example of what's called a polyalphabetic substitution cipher. So we're going to see what this means. Instead of monoalphabetic, this is polyalphabetic. Each letter, rather than being encoded, instead of all the letters being encoded with the same shift, each letter gets its own shift. Now, in this description, the version we're giving is closer to Vigenère's description of the method. The basic idea was apparently first described a few years earlier by an Italian cryptographer. But it was a little bit different, but it's very close. And so this is probably another one of those situations of a misattribution. Somebody else came up with the idea, but the person that kind of popularized it or made it easier to use it was named after him rather than the person that came up with the idea. The original version from 1553 is different but very similar in concept. Okay, so here's what we mean by encoding with a different Caesar shift. If we had just the plain text word algebra, let's say, so just that part. Well, for this cipher, we need a different key that goes with it. So we're going to have a key that I selected, is fun. So algebra is fun. And so is fun in the numerical translation becomes the I is the A is 8, S 18, F 5, U 20, N 13. And so what we're going to do is those numbers tell us which Caesar shift to use at which time. So when we're going to encode the A, we're going to use a +8 Caesar shift. The L is the next one. It's an 18. G will be +5. E will be +20. B will be +13. But then the R and the A, what do we need to do? We have to wrap back around. So the R will be a +8 and A will be a +18. And so we'll see in this example why this is a polyalphabetic cipher. When we encode this, algebra becomes IDLYOZS, and we notice that the A at the beginning is an I, but the A at the end is an S because it fell in a different place in the key. So this method lasted a long time. 1863, this code was finally broken as the fundamental idea of how to break this code was completely laid out. So if someone was using this particular method, you would be able to break this code in 1863 in a reasonable amount of time, basically paper and pencil calculations. Okay, so what happens if your key is as long as your plain text? Then there's no wraparound. But what do we have to have? What do we have to know? We have to know what the key is. And the key here, in this case, instead of just being a single character or a single number, is a set of numbers. In this case, just 5 numbers. If it were a lot of text, we would probably want a much longer key. So things that would happen with a key is you might use, if you're going to encode an entire book, you might use the first page of a different book as your key, or the first several pages of a different book as your key. And so the letters would all be encoded in different ways. Polyalphabetic, because the same letter doesn't necessarily become the same ciphertext letter, right? The letter in the plain text can become something different each time you come across it. Now, there might be some patterns, and so you might get the word algebra that just happens to line up just right in one place and lines up just right in another place as well. During the American Civil War, this cipher method was used quite often, and the part of the reason that the messages were able to be broken were that the Confederate Army used a limited number of keys, and so once they were able to break some of them, then they could, even if they didn't know what the actual, even if they found out the pattern in a different way based on other aspects, they eventually determined the key. And then if you reuse that same key, then there's no security, right? The other side, who you're not expecting to be able to read it, they can read your message because they know the key. So anybody who knows the key can read the message. And so this process here, this idea of some kind of encryption, we have going from 2,000 years ago to 500 years ago, and then again much different now, but the same kind of ideas. Polyalphabetic substitutions along with transpositions, but not just arbitrary substitutions and arbitrary transpositions, but these things done in a specific way. So as usual, feel free to ask questions in the comments, by email, or on Discord, and have a great day.